Every AI model you've ever used, ChatGPT, Midjourney, your phone's Face ID, learn everything it knows through one algorithm, one single process, and almost nobody knows how it actually works. It's called backpropagation, and today I'm going to show you exactly how it works, visually, step by step, no calculus degree required. By the end of this video, you'll understand the mechanics that powers every AI system on the planet. Before we get into backprop, let's answer a more basic question. What does it even mean for an AI to learn? A neural network is just a massive collection of numbers. We call them weights. When a network is first created, those weights are random, completely random. The network knows nothing. Learning is the process of changing those numbers very slightly and very carefully until the network starts making good predictions. Imagine you're trying to aim a cannon. At first, you fire it at random. The shot lands somewhere. You measure how far off it was. You adjust the angle slightly, and you fire again. Still off. Adjust again, fire again. After hundreds of adjustments, you start hitting the target. That's machine learning. A neural network fires a prediction, measures how wrong it was, adjusts its numbers, and tries again. Millions of times. Let's look at real networks. We'll use the simplest possible example, a network trained to recognize handwritten digits. It has an input layer on the left, 784 neurons, one for each pixel in a 28 by 28 image. The pixels come in as numbers between 0 and 1. Black is 0, white is 1. In the middle, hidden layers. Each neuron receives numbers from every neuron before it, multiplies them by its weights, adds them up, and passes the result forward. On the right, the output layer. 10 neurons, one for each digit, 0 through 9. The brightest neuron at the end is the network's prediction. This particular network has about 13,000 weights in total, 13,000 numbers that need to be tuned until the network can look at any handwritten digits and tell you what it is. That tuning process is what we're about to visualize. Every learning cycle starts with what's called the forward pass. We fed an image into the network, a handwritten 7. The pixel values flow from left to right, through every layer, through every neuron. Each neuron fires or stays quiet based on the weight sum of its input. By the time the signal reaches the output layer, one of the 10 neurons should be brightest. In a well-trained network, the 7 neuron would light up. But right now, our weights are random. So maybe the 3 neurons light up brightest, or the 9. The network guesses randomly, because it has no knowledge yet. That random guess is fine. It's where we start. The network saw the image. It produced an output. The output is wrong. But here's the crucial thing. We can't measure exactly how wrong it was. And that measurement is everything. We measure wrongness using something called a loss function. Here's how it works. The network outputs 10 numbers, one per digit. Let's say it outputs 0.5 from 0, 0.05 for 0, 0.12 for 1, 0.3 for 2, and so on. Small random values. Our target is a 7, so the correct output should be 1 for 7, 0 for everything else. We compare what the network said to what it should have said. We square the differences. We add them up. That single number, the loss, tells us exactly how wrong the network was on this one example. A loss of 0 means a perfect prediction. The higher the loss, the worse the guess. The entire goal of training is to make this number as small as possible. Not just for one image, for millions of images. We want a network that gets them all right. Now the question is, which of these 3,000 weights do we adjust, and by how much? This is where backpropagation comes in. Think of the network like a long chain of causes and effects. The output was wrong. Something in the last layer caused that. But those neurons were influenced by the layer before them, which was influenced by the layer before that, all the way back to the inputs. Backpropagation is blame assignment. Blame assignment. We start at the output, measure the error, and ask, which weight contributed most to this mistake? Mathematically, we calculate something called a gradient for every single weight. A gradient is just a number that tells you two things. 1. If you increase this weight slightly, does the loss go up or down? And 2. By how much? We can calculate this because of a mathematical rule called the chain rule. It lets us take the total error at the end and trace it backwards through every layer, splitting the blame proportionally at each step. In a single backward pass, we calculate gradient for all 13,000 weights simultaneously. We know exactly which direction to push every single number to make the network slightly less wrong. That single pass, forward, then backwards, takes milliseconds on modern hardware. Now that we have gradients for every weight, we update them. This process is called gradient descent. For each weight, we subtract a tiny fraction of its gradient. We're moving the weight in the direction that reduces the loss. Not by a lot, a tiny nudge. This nudge is controlled by a number called the learning rate. If the learning rate is too large, you overshoot. The network swings wildly and never settles. Too small and training takes forever. Get it right, and after each update, the network is very slightly better at recognizing than that 7. One forward pass, one backward pass, one tiny update to 13,000 weights. That is one training step. Now imagine doing that 6,000 times, once per image in the training dataset. Then looping through all 6,000 images again and again until the loss approaches 0. That's how a neural network learns. In practice, we don't train on one image at a time. We take a small batch, maybe 32 or 64 images, and calculate the average gradient across all of them. This is called mini-batch gradient descent. It's more stable and modern hardware handles it efficiently. One full pass through the training dataset is called an epoch. For our digit network, that's 6,000 images. We typically run dozens of edge pods. By edge pod 10, the loss is dropping fast. The network is starting to recognize patterns. By epoch 50, it's hitting 98% accuracy on images it's never seen before. And here's what I find remarkable about this. Nobody told the network what a 7 looks like. Nobody programmed the concept of an edge or a curve or a loop. The network discovered all of that automatically through mechanical process of making a guess, measuring the error, and adjusting 13,000 numbers over and over again. Backpropagation was invented in the 80s. For decades, it was considered too slow to be practical on large networks. Then GPUs got fast enough to run millions of operations in parallel. Training times went from years to hours, and suddenly deep learning exploded. Every modern AI system you use was built with some version of this algorithm. The network that detects cancer in medical scans, the model that translates between languages, the AI that writes code. All of them learn through the same fundamental loop: predict, measure, backpropagate, update. Simple idea, staggering results. If you want to go deeper, the next video covers the transformer, the architecture that made ChatGPT possible. It builds directly on everything we just covered. I'll see you there.